So welcome to lesson 8. In this first part, we will talk about a problem called counting inversions, which is very general and we can solve it in an interesting way using divide and conquer. It is covered in section 5.3 of your textbook. So the problem of counting inversions has to do with rankings. How do we compare two rankings? Suppose that we rank movies or songs or any other item. So imagine that we have n items, let's say A through E, and I order the items based on my rankings. So I have ordered A to have my first ranking, and then B, C, D, E has my last ranking, ranking 5. So I'm assuming here that the higher the number is, the lower that item is in terms of my rankings. Now, in your case, you may have a different priority, a different ranking for these 5 items. So your rankings may be, as you see here, 1 for item A, 3 for item B, and so on. Now, how do we compare these two rankings? First, notice that my ranking, in some sense, is not really needed because it is implicit based on the way that we have ordered the items. So we can strictly focus on your ranking over here and examine how often do we have a situation where an item, even though it appears before another item, has a higher rank number than the item at the right. The item C here, for instance, appears before item D, which means that according to my ranking, item C has a lower rank number, 3 versus 4, but according to your ranking, item C has a higher rank number than item D. So this is something that we call an inversion. This represents one instance of a difference between your ranking and my ranking. If you go through this list, you can see that we have in this example two such inversions, two such disagreements. One is between items B and D. Even though in my ranking B appears before D, in your ranking B has a higher rank number than D. And similarly between C and D. So we have two inversions. Now we can generalize this and define that two items, I and J, are inverted if I is smaller than J, in other words, I appears before J, but the rank that you have given to I is higher than the rank that you have given to J. A brute force obvious way to solve this problem would be to consider every pair of I and J, and of course we have in the order of n squared such pairs, and for every pair examine whether I is smaller than J, and in that case whether AI is larger than AJ, and count the inversions in this way. The question is, can we do better than that? So let's think how we could solve this problem using divide and conquer. Suppose that we are given this list of n rankings. Remember, these are according to you. My rankings are implicit on the ordering of the items. So for this n items, my ordering is basically, or my rank numbers are basically 1, 2, 3, 4, and so on. But according to you, these are your AI numbers, right? The first item, according to you, has a rank 1. The second item has rank 5. The third item has rank 4, and so on. So the spirit of divide and conquer, of course, is that you take the input and somehow you partition it into sub-problems and you solve each of those sub-problems separately. So obvious guess would be to split the input into two parts. As you see here, we have split it into the blue part and the green part, in this case exactly equal. Of course, I can do this in constant time, this division, and try to count the inversions separately on the blue part and on the green part. So imagine that this function that can solve this problem recursively gives me that for the blue array I have 5 inversions. Which are these inversions? They are between 5 and 4, 5 and 2, 4 and 2, 8 and 2, and 10 and 2. And similarly in the green array I have these 8 inversions that you see down here, say between 6 and 3 and etc. So the question is here, how would I combine these two arrays and at the same time count the inversions that happen between elements of the blue array and elements of the green array? So let's see how we can solve this problem using an idea that is quite similar to merge sort. In fact, we will actually order the elements of the two arrays, and at the same time that we are doing the sorting, the ordering, we will also count inversions. Imagine again that we have split the input into these two arrays, equal size or almost equal size, and suppose that we have already ordered the elements of the first array and of the second array. As you see, they are sorted. And suppose that we have counted the inversions that we have here and the inversions that we have here, even though I don't really show you the inversions yet. The question is, how would you combine now these two sorted arrays into a new array that is also sorted, and at the same time count how many inversions you have between the elements of the left array and the elements of the right array? So similar with what we did in merge sort, we can maintain a pointer to the first element of the left array and the first element of the second array, the right array. The only difference being that here we're also keeping track of, for the left array, how many elements it currently has. As we did in merge sort, we're comparing these leftmost elements. In the case that the leftmost element of this array is smaller than the leftmost element of this array, we don't have to do much. We just move this element down at the output array and move the pointer to the right, decreasing this length counter, the number of elements. But in this case, the opposite happens. In this case, the leftmost element of the left array is larger than the leftmost element of the right array. So this creates an inversion between the two arrays. In fact, however, it's not only one inversion. Because the elements of this array are sorted, and because there are 6 of them, if 3 is larger than 2, then we know that all of these other elements, which are larger than 3, they will also be larger than 2. So in fact, the number of inversions that we have here, it's not just 1, it is 6, because all of these elements are larger than 2. So we move the smallest element to the output array. We can now forget this element, and we write somewhere in a variable that we already found 6 inversions. At the next step, of course, we move the leftmost pointer of the right array to this element, because we're done with this. And we repeat the same process. We compare this element with this. In this case, of course, 3 is smaller, so we are moving this, move our pointer to the right. Of course, we also need to decrease the counter because now we have 5 remaining elements in this array. So now we are comparing 7 with 11. Again, there is no inversion here, so we move the 7 into the output array. Here we have 10 versus 11. Again, there is no inversion, so we move 10 to the output array. Now this gets interesting here because now we have 3 remaining elements in this array, and we're comparing 14 with 11. Again, this is an inversion, but actually it's not just a single inversion. We have three inversions because all of these three elements are larger than 11. Add them into this variable that keeps track of all the inversions. We move the 11 to the output array, and we are ready to go to the next element, which is 16. So here you see we compare 14 with 16. 14 is smaller. We move to the element 18. We only have now two remaining elements. Here we have again an inversion because 18 is larger than 16, but actually this counts for two inversions. So we continue as you see in the animation. And as you see in the rest of the execution, there are no more inversions. So at the end of this process, we have found that there were 13 inversions between the elements of this array and this array. And in the process of creating this output array, notice that we have actually sorted the two arrays. So let's now look at the pseudocode, the algorithm for the idea that I just described before with an example. This function that does what we just discussed is called merge and count. It receives two arrays A and B that, remember, we are assuming here that they are already sorted. And we maintain, of course, a current pointer for each of these two arrays that is initialized at the front element, the leftmost element. And we also maintain a variable count for the total number of inversions that we have seen when we are merging A and B. And of course, that variable is initially 0. So most of the work is done here at the while loop. As I described before, we're comparing the elements A, I, and Bj, which are the elements of the arrays A and B that are pointed by the current pointers. And we put the smallest of the two elements in the output array. But if the smaller element is Bj, the one at the right array, then we increment count by the number of elements that are remaining in the A array. Right? This is when you have inversions and you have to increment count not only by one, but by the length of the array A. Else, if AI is smaller than Bj, then of course you don't have to increase the variable count because there are no inversions. You just advance the current pointer of the appropriate list, either A or B, depending on which element was smaller. Now, if at some point one of the lists is empty, then you just move the remainder of the other list to the output, and you don't have to change the count of inversions. So what comes out of this function, right, is an ordered, a sorted list that includes all the elements of A and B, and a variable count that keeps track of how many inversions we had between the elements of A and B. So now we are ready to look at the complete algorithm. Let's call this sort and count. I give you again an array of n elements, and if we're in the case that this array has only one element, then we don't need to do anything basically. We just return that same array and we say that there were 0 inversions. On the other hand, if the array L has more than one elements, then this is where the recursion happens. This is where the divide and conquer happens. We split the array L into two halves, A and B, and we call this same function sorted count. We call this same function separately for A and for B. This function will do two things. It will sort the array and it will also count the inversions in A, and similarly for B. Now, when we're at the point that both of these recursive functions have returned, in other words, now A and B are sorted, we can call the function I showed you earlier, the merge and count function, on these two sorted arrays A and B, merge them into the array L, which will also be sorted, and in parallel we're counting the inversions that happen between A and B. So finally, we're ready to return the total number of inversions in the array L. What is that total number? It's the number of inversions that we had in A when we were processing A, the number of inversions we have in B, and the number of inversions we found when we were merging A and B. Finally, we are ready to talk about the running time of this algorithm. So as we do with merge sort, we split the problem of size n into two problems of size n over 2. So if t of n is the time to solve the problem of size n, we now have to solve two problems, each of them of size n over 2. And what does it mean to solve them? It means basically to sort the corresponding array and at the same time count the number of inversions in that array. So for instance, this is how we would get that the blue array has 5 inversions and the green has 8. But then, as we discussed before, you have to merge these two arrays and at the same time count how many inversions they have using that merge and count function. And that function takes linear time because remember we were going through each of the elements of the blue and the green array only once. So the time to combine the solutions is big O of n. Now this is exactly the same recursion we had with merge sort. So if you want, you can just tell me that the running time should be the same, big O n log n. Or of course you could use the master theorem and the case of alpha equal 2, beta equal 2, and gamma equal 1 would also give us the same asymptotic running time.